But we're going to move on now to Paul Bellan, who's going to be discussing an instrument design that has been developed for lunar probes. Paul, it's yours.
I'll say that this is work done by myself and Gianluca Delzano at Los Alamos. We worked on this for the last, I guess, year and a half as part of a science definition team set up by Insob Han. Okay. So can you go back to the title slide? Yes. So we call this the Plasma Lunar Surface Probe, or the acronym is PLUS probe. And next slide, please. So again, we're showing a picture of astronaut Harrison Schmitt with a dirty spacesuit because of dust on it. And as has been mentioned many times, dust is important. Next slide, please. So the dust, oh, go back. Okay. So the moon isn't the only place that doesn't have an atmosphere. There are plenty of airless bodies out in space, Mercury and the asteroids. So whatever we find on the moon might be relevant to these other bodies. Okay, next slide. So I think this picture was shown earlier by Christine, but there were photographs of glows above the horizon, and they were postulated as being dust, and then there were also counter arguments, but there is some confusing data on whether or not there is dust on the moon, and so the goal is to find out whether there is or there isn't. Next slide. So the situation is actually pretty complicated. If you look at the picture on the right, there are different colors that I'll refer to. So we'll start with the yellow solar wind electron. So the solar wind is coming in all the time from the sun, and it's a plasma that consists of electrons and ions. And so there's ions and electrons from the solar wind, and then at the bottom right, you see a picture of the sun and a little wiggly arrow saying UV light. So there's UV light coming from the sun also. So the UV light hits the sun, and that causes photoelectrons to be emitted. Those are shown by the little blue dots with minus signs on them. And so you wind up with a cloud of electrons above the lunar surface, but since you've removed these electrons, there's a deficit of electrons in the surface, and the surface is charged positive. So if we go up to the solar wind ions, shown as the mauve or purple arrows on the right, the ions are positive, and they're coming in, and the lunar surface is positive. So the less energetic ions will be repelled from the surface, and that's why you see a mauve line coming in and then turning around and going back. But then the more energetic ones can make it to the lunar surface. And then if we go down a bit to the yellow, the solar wind electrons, they're negative. So they see this cloud of electrons above the surface, and so they're repelled by that. So that shows some of them turning around by the cloud, but if they're energetic enough, then they can make it and hit the surface. And then there's the dust shown as green, and the dust can get charged up negative by the little blue circles that are sitting just above the surface. Those are the electrons that have been kicked off by photo emission. The dust itself can be hit by sunlight and emit photoelectrons and then become positive. So practically everything can happen everywhere, and all this will set up electrostatic potentials and electric fields, which will then provide forces on the dust. You can also get into a situation where all the free electrons get stuck to the dust, And then you have a weird kind of plasma where the heavy particles are the negative dust grains and the light particles are the positive ions. And then furthermore, there's gravity that tries to make the dust fall down. And if the electric field is oriented the right way and the dust grains are charged the right way, that could push the dust grains up and you could get a levitation or lofting, as Christine mentioned. So there's lots of equations that can be written to describe all these interactions. Next slide, please. So John Luca wrote out those equations and solved them numerically. And the left shows the electrostatic potential in volts.
Excuse me, Gennady Dolnikov, could you please mute your mic? Gennady Dolnikov, could you please mute your microphone?
Yes.
Thank you.
Okay. There's still some background. Could people mute their microphones? Okay, I'll continue. So there's an electrostatic potential shown on the left graph versus altitudes in meters. And you see that on the far left, the voltage is positive, around 4.5 volts. So that the lunar surface is positive from the photoemitting electrodes. But then there was a cloud of electrons above the surface. And so you can see the potential is below zero. And that's from this negative cloud of photoemitted electrons. And then on the right graph, that's density of particles versus altitude, now on a logarithmic scale. And the blue line shows the electrons with the cloud above the surface. The green line is the solar wind ions coming in at high velocity. And then the red is solar wind electrons, which are getting repelled by the cloud sitting above the surface. Okay, next slide. So all this is nice theory, but these are predictions only, and we really don't know whether this is correct or not. We can sit and model as much as we want, but who knows whether this is right or not. Next slide, please. So we need to measure to find out what is really going on. That's the only way to know for sure. And then, of course, the measurements might detect something we never thought of, and then that will go into the model. And eventually one hopes to have measurements and models that agree with each other. Next slide. Furthermore, the model, and presumably what happens, depends on the solar angle, because if the sun isn't shining, then we don't get the photo emission. And if the sun is low in the sky, then we'll get less photo emission. So everything I showed you there is going to be a function of time in the lunar day, whether the sun is high in the sky or just on the horizon or not there at all. Next slide. So the obvious diagnostic to make the next step is a Langmuir probe. A Langmuir probe is a very simple gadget in principle. You put a piece of metal in a plasma and you bias it to a sequence of voltages, and then you measure the current that you collect. You get an IV characteristic, current voltage characteristic. And there are theories that show that you can deduce the electron density, the electron temperature, and the plasma potential by the nature of that characteristic. Langmuir probes are very old. They were invented by Langmuir about 100 years ago, around 1920. And they've been used on spacecraft for over 60 years. And of course, they've been used in the lab for about 100 years. So I've shown a sketch of the basic Langmuir probe idea. The horizontal axis is the probe bias, where 0 means the probe is biased to the potential of the plasma. And so the probe could be biased negative relative to the plasma. That would be to the left of 0, or it could be biased positive relative to the plasma. That would be to the right of 0. And when you go through the detailed physics, you find that if the probe is biased negatively, then it repels electrons, and there's an exponential behavior of the current. But if it's biased positively, then it attracts electrons, and there's a different kind of behavior that depends on electron orbits, somewhat like the comets orbiting around the sun and maybe coming in and hitting the sun, and you count up the number of comets that hit the sun. So there's a change in the behavior, and if you can detect the region where there's the change in the behavior, the transition from exponential to non-exponential, that gives you the plasma potential. The behavior of the exponential region, how exponential it is, gives you the electron temperature. And then the height, the amount of currents you collect at the plasma potential, gives you the electron density. Next slide, please.
5 minutes.
Okay, so the issues are the lunar situation is very different from lab and space, and the design of the probe depends on plasma parameters. But now we have a quandary because we don't know the plasma parameters. So how can you design something to measure the parameters if you don't know what they are? But generally, a lower density requires a bigger probe to collect enough current. In the lab, probes are millimeters in size. In space, on spacecraft, probes can be tens of meters in length, and but a nearer spacecraft, the probe could be centimeters in dimensions. Next slide. So a major issue is that the probe will also have photo emission, and the photo emission current turns out to be about 5 times as big as the Langmuir probe current. So we need to shield the probe from sunlight and even from reflected sunlight or moonlight. Next slide. So here's a sketch of what the probe might look like. There's a sun shield and a moon shield to avoid the light, and then the surface is made of 2 types of material, one that will absorb photons and one that's more mirror-like and reflect photons. And by looking at the difference between those, we'll be able to figure out how many photons are being emitted because of sunlight. Next slide. So this shows that this graph, if there's a reflecting surface, you get one kind of Langmuir probe profile, and if you get an absorbing surface, you get a different kind. And if you look at the difference between the two, you can figure out what the sunlight is doing and then get rid of it and get a true Langmuir probe profile. Next slide. And then the probe will have dimensions about the size of a gallon of milk, and so there'll be enough room inside the probe to put the electronics inside the probe, and that will be good because the currents are very small and we need to avoid spurious currents, and this will provide intrinsic shielding. Next slide. And there will be electronics to measure the currents going to every single surface on the probe, and then they'll all be biased in controlled ways. And by biasing everything every which way and measuring the currents every which way, we'll be able to figure out what's going on. The communication will be via optical fiber. The idea is to avoid wires going to the probe as much as possible, so as to avoid spurious currents. We'll be measuring picoamperes probably. Next slide. And then the probe ultimately would be mounted so that it could be moved to different altitudes above the lunar surface. And then by measuring the plasma potential at different altitudes, the gradients of that plasma potential would give you the electric field. And then we would know whether there's a strong enough electric field to compete with gravity and levitate things. Also, the probe will be arranged so that it could point at the sun. So the sun shield will be like a parasol that will prevent sunlight from hitting the probe, so you don't have photo emission from the probe. Next slide. Another way of operating the probe is as an impedance probe. This is a completely different technology. In this technology, one biases the probe at different frequencies and looks for a resonance. The plasma around it has a characteristic frequency called the plasma frequency. And if the probe is oscillated at the plasma frequency, its impedance will go up. And so one can get the density that way. So we would have 2 independent ways of measuring the plasma density, and that would provide confidence that we have a good measurement, because otherwise we'll just get a number and we won't know whether that's the right number or not. But if you do it 2 different ways, then you would think that, yes, this is correct. Next slide. So conclusions are that the dust is an important issue for lunar exploration, but the way the dust behaves, at least above the surface, is largely governed by plasma, but we have only the foggiest idea of the plasma parameters. They're not now known. And whatever is going on is a complicated mix of the solar wind, the dust, ultraviolet light, incident angles. And this plus probe would enable first determination of the main parameters, and then we get a handle on what the dust and plasma are doing, what the dust is doing. So then the probe design and interpretation has been supported by detailed modeling so far, but we would have to make measurements and further connect it to the modeling. So that's it. Thank you very much.
It looks like we're right at time.